All right, so tonight we want to talk about limits. So the idea of a limit is that the value for f of x may not exist, but we don't actually care about the value of f of x. What we care about is what is f of x approaching as we get really close to this value. So we're looking at what happens to x as we come at this value that we're looking at as we're approaching some given number, some given number. As x approaches a, as x gets closer and closer to a, what is happening to our function? What number is our function approaching? And as we approach a from the right-hand side, what is happening? As we get values closer and closer to a, what is happening to the value of the function overall? Okay, so we don't necessarily care about what is happening at that specific point. It might not even be possible to figure that out, but we care about what is happening as we approach that number. Okay, so as x approaches a, that means our input gets closer and closer to this value that we want to use as our input. The limit of f of x is L. If the limit from the left exists and the limit from the right exists. And I want to show you let's go to full screen here. Okay, I want to show you the notes for that. Okay, so this line, that little negative, this a with that negative, that is not an exponent. That means as x approaches a from the left, that means numbers we typically think of as negative numbers. So we're coming at it from that negative side of the graph. The numbers may not actually be negative, but it's the side where the numbers are less than a and getting bigger. Okay, so this is the approaching from the left. This plus sign on number 2 means we are approaching from the right. So we're starting as numbers where x is bigger than a and coming back toward it. If we find the limit from the left and from the right, and they are the same number, then we say the overall limit exists. Okay, and I will show you how to do that in just a minute. Okay, so here's our first question. What is f of 3? Can I plug 3 into this function? Okay, if you remember the review chapter, we said we couldn't have a 0 in the denominator of a fraction. And if I plug 3 in here, I get 3 minus 3 in the bottom. So the bottom of my fraction would be 0. So f of 3 does not exist. Okay, it's undefined. That does not mean that this function does not have a limit. Okay, so the way you would find this, you're going to put this into your calculator. You're going to use the y equals button on your calculator, and you're going to type in parentheses, make sure you have these parentheses, x squared minus 9, close parentheses, hit the division button on your calculator. On your screen, it will actually show up as a slash like that when after you type it in, you'll see a slash. Parenthesis again, x minus 3. If you do not put those parentheses where I've placed them, you will get the wrong answer. Remember, you type in the division sign, but it shows up on your screen as that slash. Okay, so you're going to type this into the y equals, and then what we're going to do is go to our table of values. And when we look at our table of values, let's see if we have a table of values on the next screen. There we go. So when we look at the table of values, when we're coming at it from the left, that means numbers that are smaller than 3. So what we want to do is start smaller than 3, but get closer and closer and closer and closer to 3 without ever using the number 3. we started at 2, 2.5 is a little closer to 3, 2.9 is even closer, 2.99 is even closer, 2.999 is even closer. You could keep going if you want and plug this into your calculator. Okay, you're going to want to be able to plug these numbers in your calculator. So I will pause in just a minute and explain to you how to change your calculator settings so that you can plug numbers in. But what we see here is when we plug 2 in, we got 5. Then when we plug 2.5 in, we got 5.5. 2.9 was 5.9. 2.99, 5.99. 2.9999, 5.999. Okay, so it appears that the value is approaching 6. The closer I get to 3 from the left with my x's, my y value is approaching 6. Okay, if we go the other direction, so this time we're approaching from the right. So we want to start with numbers bigger than 3, so 4, and go closer and closer in 3. So this time we're going to come down a value. So we started with 4, we got out of 7, we used 3.5, got 6.5, 3.1, we got 6.1, 3.03, 6.01. So again, it looks like we are approaching 6. Since both limits were 6, that means the overall limit is also 6. And I'm going to pause here, insert a blank page, because I want to explain to you how to set your calculator so that you are able to enter values in. Right now, if you hit y equals, and if you hit second, which is your blue key, and the graph button, you should get your table of values. Okay, so you get to the table, by hitting second, graph. Okay, remember this only works when you have a value in an equation in y equals. Okay, but right now when you hit second graph, your table probably looks something like this: x, 0, 1, 2, 3, 4, and then it'll give you the y values associated with it. But we didn't want whole numbers. We want to be able to put any numbers that we want in. So what you need to do is change this. And we're going to do that. You're going to hit second, second, and the window button. You'll notice in the blue above that it says table set. On the screen now, you should see table setup. It'll say table start. Doesn't really matter where it's starting. So let's just say it says 0. That's fine. You can leave it at that. It says change in table equals 1. That's fine. You can leave it at that. Then it says independent. Dot, dot. And it has auto and ask. And dependent, auto, and ask. Right now, if your table looks like this over here, then probably what has happened is these are both set to auto. And what we want to do, let me see if I can pull up a highlighter here. Highlighter. What you want to have highlighted on your screen, so move your cursor so that it highlights it. Oops, hang on one second, that didn't work. Highlighter. There we go. You want to have ask highlighted for independent, Leave auto highlighted for dependent, otherwise it's not going to calculate your output value. So this here, this was probably on auto. You need to switch it so that ask is highlighted. Then when you go back to your table, when you go back to your table of values here, it will be completely blank if you've never done this before until you start entering values in here for X. Okay, so this is how you're going to set up your table so that you can enter any values in that you want. All right. On a graph, we can see limits. So we have this particular graph here. Here is our A value. We've got a hole in the center of that graph. That means that A value doesn't exist. But what happens as we approach that value from this side? What is our Y value? And you can see our Y value is approaching 3. So as we approach the X value of 2, our Y value approaches 3 from the left. When we approach from the right, again, as we are approaching that X value of 2, our Y value is approaching 3. So again, the limit as X approaches 2 of f of X is 3. Okay, so let's look at this function. The limit of f of X as X approaches 3. Okay, again, you're going to want to set up a table of values. You're going to want to put this in your Y equals. So Y equals, on your calculator, 1 divided by X minus 2. And then outside the parentheses by itself, you'll have the plus 2. And we're going to want to have a table of values that looks something like this. Oh, we've got the function right there. So X, Y, let's see, 2, 2.9, 2.9, oops, 99, 2.999, 2.99999. Do it until you see a pattern emerge. Same thing from the other side. X, we're going to want to start at numbers bigger than 3. So that would be like 4, 4.1. Sorry, going the wrong way. Sorry, 3.1 I meant to say. 3.01, 3.001. Okay, so you're going to want to see what happens in your table of values as you approach those numbers. And if we go to the next screen, we can see a table here. It looks like as we approach from the left, we're approaching the value of 4. So as we're approaching the X value of 3, our Y value is getting closer and closer to 4. And as we're approaching the X value of 3 from the right, our Y value is again getting closer and closer to 4. Now let's go back to the other page. Okay, the other question was the limit of f of X as X approaches 2. So again, we're going to want that table of values. X is approaching 2 this time, so we might want to start at 1.9. I'm just going to go ahead and start at values really close to 2, but smaller than 2. Okay, you might even 9999. Okay, and then numbers bigger. So what a number bigger than 2? Well, 2.1 is bigger than 2, but really close to it. 2.01 is even closer. 2.0001 is even closer. 2.00001 even closer. Okay, so those are the kinds of values you're going to want to put in your calculator. Go ahead and put those in and see if you can see a pattern emerging. Go ahead and pause the video while you do that. I'm going to skip ahead to another slide though. Okay, so Here we have 1.9, 1.99, 1.999. What is happening as we approach 2 from the left-hand side? The closer we get to 2, this is becoming a really large negative number, and it doesn't look like it's going to stop. And if you need to see that, then put a number like 1.9999 into your calculator and see what you get. This is going to keep growing, so we're approaching negative infinity. When we approach this from the other side, so we started at numbers bigger than 2, then 2.1, 2.01, 2.001. Again, these numbers keep getting bigger. And if you want to see what happens next, put in 2.0001 and keep putting bigger numbers closer and closer to 2 in there. And what you're going to see is this, sorry, let's move those out of the way, is going to approach positive infinity. Okay, positive infinity and negative infinity are not the same thing, so the limit does not exist. Okay, again, we can see all of that in our table of values. Okay, one more thing we want to do with this. This time we're going to do something a little different. We want to find the limit as x approaches infinity. Okay, that means I want this value to get really, really, really large and see what happens. Okay, so again, we should already have this function in our y equals. But when we go to do our table of values, and this is completely up to you how you start. I usually like to start with kind of a big number and then get more and more ridiculous. Okay, and I might just go really ridiculous, right? I'm trying to get to infinity. I'm trying to make really, really big numbers. Okay, and then let's see what happens here. Okay, so we're putting in bigger and bigger and bigger numbers until you see a pattern emerge. So as we put in bigger and bigger and bigger numbers, what are you seeing? We should see that as the numbers keep getting bigger and bigger and bigger. Now, the one thing I should mention is, since we are going toward positive infinity, okay, so if you think of a number line, here's negative infinity, here's positive infinity. Positive infinity can only be approached from the left. I can't go over here and get around to the other side of infinity and come back at it. Right? I can't ever get to infinity, so we can't approach it from the right because you can't get bigger than infinity to come back to it. So this is going to be a one-sided limit. Okay, so as we approach it from the left, you'll notice the values seem to be settling down at 3. And again, put bigger numbers in and make sure that that pattern is what you see if you're not comfortable with that. Okay, so for this one, the limit as x approaches infinity is 3. Okay, some limit properties. Okay, so these are just properties. You're probably going to use a lot of them without even knowing that you're using them. Okay, the limit of a constant is that constant. So let's think about a constant function, which is something like y equals 5. Okay, if I put in x values of, doesn't even matter, 0, 1, 2, doesn't matter what you put in, the answer is always 5. It doesn't change. So the limit of a constant is always going to be the constant. For this function, since it is always 5, no matter where you are, the limit has to be 5. Other limit properties. The limit of a power function is the limit of the base raised to that power. Okay, so for example, I can take the limit of f of x raised to a power, or I can take the limit of just f of x, get an answer, and raise the limit to the power. Okay, it depends on which one's easier. Okay, the same idea holds true for roots. So I can take my function and raise it to the power first and take the limit of that whole thing, or I can take the limit of just the function and then raise the limit to the power. That's what that property is saying. The next one is the limit of a sum. Okay, so the limit of a sum or difference is the sum or difference of the limit. So if I'm taking the limit of something where there's two functions added together, if it is easier, I could take the limit of one function and okay, so the limit of a sum or difference is the sum or difference of a limit, as I was saying before we got interrupted. If you have two things being added together or subtracted, and you're taking the limit of the sum of those, you can take the limit of one and then the limit of the other and add those two limits together. The limit of a product, multiplication, is the product of the limit. Again, if you're multiplying two functions together and you want to take the limit of that whole thing, it is the same as taking the limit of the first function, taking the limit of the second function, and multiplying those limits. Limit of a quotient is the quotient of the limits. So again, rather than taking the limit of this fraction, we would take the limit of the numerator, take the limit of the denominator, and divide those. Now remember, got to remember that m can't be 0 because that would give us something that is undefined. And our last limit property is that the limit of a constant times a function is the same as if we pull that constant out in front and take the limit of the function and then multiply that limit by the constant. Again, you're probably not going to think about these when you use them, and you're not even going to realize that you're using them, but we do need to mention what they are. Okay, so here is an example where we are going to use limit properties. So here, if you take the limit of this function, we would take the limit of x squared, and actually we could take the limit of just x, and then we can square that, so that's going to be 16. Then we're going to take the limit of this constant times the x, and then of course that's the limit of the constant. We're not going to do all that right now, but if you go through these slides, they define for you how they used each of those properties. All right, we do have this theorem of limits of rational functions. So for any rational function, if a is in the domain, and remember, if it's your domain is going to be all real numbers unless it's a fraction or a square root. So if a is in the domain, instead of having to do those tables, we can plug a straight in, and that will be our limit. Okay, so if a is in the domain of your function, you can plug it straight into the function to find your limit. That's what the limit of rational functions theorem tells us. Okay, so that's going to make life a lot easier because some of these we're going to be able to plug the number straight in. So for example, let's look at this one. Is 0 in the domain of this function? Well, the easiest way to tell with a square root is plug it in. Let's see. As long as it doesn't end up negative, then it's in the domain. So 0 squared minus 3 times 0 plus 2. So it looks like we have square root of 2. So it is definitely in the domain, which means your limit is the square root of 2. Okay, so you can try these on your own. Remember, you'd plug 1 in and see what the answer is to get the limit. Plug 4 in. 4 is in the domain here because 3 times 4 is 12 minus 2, that's 10. So I don't get a 0 in the denominator here, so that's fine. So all 3 of those should, and don't worry about the limit properties, should be able to be worked using that theorem on rational limits. Okay, here's an interesting one though. Is -3 in the domain of this function? Remember, when you're looking at a fraction and you're checking for domain, take that denominator, set it equal to 0, and let's see what happens. Okay, it's not in the domain. -3 plus 3 is going to give me a 0 in the denominator. So when I want to take this limit, I've got to go back to, okay, so I don't really want to do a table of values if I don't have to. I mean, they're easy enough, but is there another way? So let's pay attention to this top part. X squared minus 9, that factors. That factors to x plus 3, x minus 3, and that's divided by x plus 3. So we can simplify this fraction. They both share a factor top and bottom. So that's going to simplify down to x minus 3. So can I plug -3 into this? And the answer there is yes. So now all I have to do is say, oops, so sorry, the limit as x approaches -3 of x minus 3. So that's going to be -3 minus 3 is -6. Okay, so if you can simplify it down, then we can still use that theorem on the limit of rational functions. And this should look very similar to that very first problem we did tonight. Okay, the last thing we have to talk about is continuity. A function is continuous at a specific number if f of a exists. That means we have to be able to plug f of a in and get a number. If the limit of, as x approaches a, of f of x exists, and then the limit and the actual output have to be the same number for it to be continuous. Put that there, because I am done.